In this video, we'll look at two key concepts that describe the variability of data: homoscedasticity and heteroscedasticity. We'll see how to detect non-constant variance with the Breusch-Pagan test and cover measures for addressing it. Let's start with homoscedasticity. This is a term used to describe a situation where the variance of the residuals is constant across all levels of the independent variables. In other words, no matter what value the predictor variable takes, the spread of the residuals remains consistent. One of the key assumptions of the classical linear regression model is that the error terms, epsilon I, are homoscedastic, meaning they have a constant variance, sigma squared, for all I. Consequently, it follows that the variance of the response, yi, is also sigma squared. Let's see why. Consider the simple linear regression equation. Yi equals beta 0 plus beta 1 xi plus epsilon I. Taking the variance of both sides, the variance of yi equals the variance of beta 0 plus beta 1 xi plus epsilon I. Since beta 0 plus beta 1 xi is a fixed quantity given xi, it does not vary. So the variance of yi is due solely to the variance of epsilon I. This gives us our result. The variance of yi equals the variance of epsilon I, which is sigma squared. This derivation also holds true for multiple linear regression. Heteroscedasticity, on the other hand, occurs when the variance of the residuals is not constant across all levels of the independent variables. In other words, the spread or dispersion of the residuals changes as the value of the predictor variable changes. Let's compare the two side by side. Under homoscedasticity, every error term has the same constant variance, sigma squared. Under heteroscedasticity, the variance changes from observation to observation. We write this as sigma I squared, where the subscript I indicates that each observation can have its own variance. This non-constant variance violates the Gauss-Markov theorem and can lead to issues in regression analysis, such as unreliable standard errors and inefficient estimates. To better understand these concepts, let's look at some plots. First, the homoscedasticity plot. The residuals are scattered evenly around the regression line, with no pattern and a consistent spread across the entire range of the predictor variable. Now compare that to the heteroscedasticity plot. Here, the spread of the residuals changes with the value of the predictor. Notice how the points hug the line tightly on the left, but fan out as x increases. This funnel shape is the classic signature of heteroscedasticity, and it suggests that the assumptions of the ordinary least squares model are violated. Another useful way to diagnose this is with residual plots. Let's plot the residuals for the same data against the predictor. On the left, the homoscedastic residuals are scattered evenly around 0, with no discernible pattern and consistent spread across the range of x. This confirms the presence of homoscedasticity. On the right, the heteroscedastic residuals show a clear pattern. The spread increases as x increases. The variance of the residuals is not constant, which indicates heteroscedasticity. Once again, we see the funnel shape opening up to the right. When you spot this pattern in a residual plot, heteroscedasticity is likely present. The Breusch-Pagan test is a statistical test used to detect heteroscedasticity in a regression model. The test is based on a simple idea. If the variance of the residuals is constant, then the standardized squared residuals should not be systematically related to the independent variables. So we regress the standardized squared residuals on the independent variables and check whether there is a significant relationship. A significant relationship indicates heteroscedasticity. The null hypothesis states that gamma equals 0, where gamma is a vector of parameters to be estimated. This means the variance of the residuals is constant, so we have homoscedasticity. The alternative hypothesis states that the variance of yi equals sigma squared plus zi prime gamma, where zi is a vector of the independent variables. In other words, the variance of the residuals depends on the independent variables, and we have heteroscedasticity. The test has 5 steps. Step 1. Run the regression model and obtain the residuals, ei. Step 2. Compute the squared residuals and standardize them by dividing by the estimated error variance, s squared. This gives us ei star squared. Step 3. Regress the standardized squared residuals on the independent variables zi. Step 4. Calculate the test statistic, Lm, which equals the regression sum of squares from step 3 divided by 2. Step 5. Compare the test statistic to the chi-square distribution with degrees of freedom equal to the number of predictors p excluding the intercept. If the p-value is less than the chosen significance level, we reject the null hypothesis of homoscedasticity, indicating the presence of heteroscedasticity. One quick note. Since the alternative hypothesis implies a specific direction, increasing variance, the test uses the upper tail of the chi-square distribution, making it one-sided. Let's work through an example of the Breusch-Pagan test. We are given a small dataset with an independent variable x and a dependent variable y, with 5 observations. We assume the fitted regression equation is y equals 1.8 plus 0.68x, and the estimated error variance, s squared, is 0.06. We're also told the regression sum of squares from regressing the standardized squared residuals on x is 4. Our goal is to compute the standardized squared residuals, calculate the test statistic, and determine whether we reject a null hypothesis at the 5% significance level. Step 1. Run the regression model and obtain the residuals. For each observation, we compute the predicted value from the fitted equation and subtract it from the actual value. For example, for the first observation, the predicted value is 1.8 plus 0.68 times 1, which is 2.48. So the residual is 2.3 minus 2.48, which is negative 0.18. Repeating this for all 5 observations gives us the residual column. Step 2. Compute the squared residuals and standardize them by dividing by the estimated error variance of 0.06. For the first observation, negative 0.18 squared is 0.0324, and dividing by 0.06 gives 0.54. Doing the same for the remaining observations, we get 2.16, 0.96, 0.01, and 0.17. Step 3 would be to regress the standardized squared residuals on x, which is typically done using software. We can skip this step since the regression sum of squares is provided in the question. Step 4. Calculate the test statistic. Lm equals the regression sum of squares divided by 2, which is 4 over 2, giving us a test statistic of 2. Finally, Step 5. Compare the test statistic to the chi-square distribution with 1 degree of freedom, since there is one predictor, x, excluding the intercept. The critical value at the 5% significance level is approximately 3.841. Since 2 is less than 3.841, we fail to reject the null hypothesis. Therefore, there is no evidence of heteroscedasticity in this regression model. So what do we do when heteroscedasticity is detected? There are 3 remedial measures we can take to address the issue. The 3 remedies are heteroscedasticity consistent standard errors, weighted least squares, and transformation of variables. Let's start with heteroscedasticity consistent standard errors, also known as robust standard errors. Heteroscedasticity consistent standard errors adjust for heteroscedasticity without modifying the coefficients themselves. Unlike ordinary least squares standard errors, which assume constant error variance, these methods correct the standard errors by considering the actual variability of the residuals. The robust standard error of the coefficient bj is the square root of the j plus first diagonal element of the estimated variance-covariance matrix of the coefficient estimates. Here, var hat of b represents the estimated variance-covariance matrix of the coefficient estimates, adjusted for heteroscedasticity. The reason we use the j plus first element is that the first diagonal element corresponds to the intercept, b0. The second remedial measure is weighted least squares. This method assigns different weights to observations based on the variability of their residuals, giving less weight to observations with higher variance. Weighted least squares is an extension of ordinary least squares that accounts for heteroscedasticity. It minimizes the sum of squared residuals, where each residual is weighted by the inverse of its variance. The weighted least squares estimates of the coefficients beta are given by this formula: x transpose wx inverted times x transpose wy, where x is the matrix of independent variables, W is the diagonal weight matrix whose elements Wi are the inverse of the error variances, and y is the vector of dependent variables. The key idea is that by weighting the variables with the inverse of the error variances, we convert the original heteroscedastic regression problem into one where the errors have constant variance, so ordinary least squares can be applied to the transformed data. The third remedial measure is the transformation of variables. Transforming the dependent variable y can effectively address heteroscedasticity by stabilizing the variance of the error terms. Using the natural log of y is particularly effective when the dependent variable is strictly positive and exhibits multiplicative heteroscedasticity, where the variance of the errors increases proportionally with the level of y. This transformation compresses the scale of larger values more than smaller values, which reduces the relative variability. What if the data has zeros or negative values? Adding a constant can make all observations positive before applying the transformation. For instance, the transformation log of 1 plus y can handle zeros in the data. Additionally, multiplying by a constant helps retain the data's approximate original units. For example, this transformation, 100 times log of 1 plus y over 100, is used for percentage data, where negative values may occur. A few limitations to keep in mind. Power transformations, like the logarithmic transform, are not effective for non-monotonic variability patterns. They are also not helpful if the data is symmetric but heteroscedastic, as the transformation could distort the distribution. Finally, transformations of independent variables are also valid for addressing heteroscedasticity, but could be less interpretable if regression assumptions are violated. And that wraps up our chapter on heteroscedasticity. We learned how to detect it visually and with the Breusch-Pagan test, and how to address it with robust standard errors, weighted least squares, or a transformation of variables. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.